x, and then it jumps up to this interval for x, and then it jumps back down. By now, we're used to seeing functions defined like h of y is equal to y squared, or f of x is equal to the square root of x. What we're now going to explore is functions that are defined piece by piece over different intervals. And functions like this are, you'll sometimes view them as a piecewise, or these types of function definitions, they might be called a piecewise function definition. And so let's take a look at this graph. This graph, you can see that the function is constant over this interval for x, and then it jumps up to this interval for x, and then it jumps back down for this interval for x. So let's think about how we would write this using our function notation. So if we say that this right over here is the x-axis, and if this is the y is equal to f of x axis, then let's see, our function f of x is going to be equal to, let's see, there's three different intervals. So I'll give myself some space for the three different intervals. Now this first interval is from not including negative 9. I have this open circle here, not a closed-in circle. So not including negative 9. But x being greater than negative 9, and all the way up to and including negative 5. So I could write that as negative 9 is less than x, less than or equal to negative 5. That's this interval. And what is the value of the function over this interval? Well, we see the value of the function is negative 9. It's a constant negative 9 over that interval. It's a little confusing because the value of the function is actually also the value of the lower bound of this interval. It's very important to look at that this says negative 9 is less than x, not less than or equal. If it was less than or equal, then the function would have been defined at x equals negative 9, but it's not. We have an open circle here. But now let's look at the next interval. The next interval is from x is greater, or negative 5 is less than x, which is less than or equal to negative 1. And
What's it going
over
to say?
that interval, the function is equal to, the function is a constant 6. It jumps up here. Sometimes people call this a step function. It steps up. It looks like stairs to some degree. Now it's very important here that at x equals negative 5, for it to be defined only one place. Here it's defined by this part. It's only defined over here. And so that's why it's important that this isn't a negative 5 is less than or equal to. Because then if you put negative 5 into the function, this thing would be filled in, and then the function would be defined in both places, and that's not cool for a function. we've taken equations like this and tried to, quote, solve for x. What we're going to do in this video is deepen our understanding a little bit about what's going on and really think about the notion of equivalence or equivalent statements. Let me write that down. Equivalence. Now, what do I mean by equivalence? Well, I'll use this equation here to essentially keep rewriting it in equivalent ways, and I'll talk a little bit more about what that means. So one thing that I could do to essentially write the same equivalent statement is I could distribute this 3 onto the x or onto the x plus 1, and then this part of it could be rewritten as 3x plus 3, and then we have minus x is equal to 9. Now, what I will say, or what it might be obvious to you on some level, is this top equation and this second equation are equivalent. What does that mean? It means if one of them is true for a given x, the other one will be true for that same x as well, and vice versa. And we can write other equivalent statements. For example, if we were to combine x terms here, if we were to take 3x and then minus x right over there, I could rewrite that as 2x, and then I have plus 3 is equal to 9. Now, all three of these statements are equivalent. If there's an x where 2 times that x plus 3 is equal to 9, then it is also the case that 3 times that x plus 1 minus x is equal to 9, and vice versa. If there's some x that would make this top equation true, then it's going to make this last equation true. And we can do other equivalence preserving operations, and you've seen them before. You could subtract 3 from both sides. In general, if you are adding or subtracting the same value from both sides, it is equivalence preserving. If you are distributing a value like we did at that first step, that is equivalence preserving. If you combine like terms, so to speak, that is equivalence preserving. And so here we'll do an equivalence preserving operation. We'll subtract 3 from both sides, and you would get 2x is equal to 6. And once again, any x that satisfies this last equation will satisfy any of the other equations, and vice versa. Any x that satisfies any of these other equations will satisfy this last one. And so they are all equivalent to each other. And then another equivalence preserving operation is to multiply or divide both sides by a non-zero constant. And so here we could divide both sides by 2. 2 is not 0, it's constant. And if we did that, we will get another equivalent statement, that x is equal to 3. So any x that satisfies this, and there's one, x equals 3, would satisfy the other ones, and any x that satisfies any of the other ones would satisfy this last one. So these are all equivalent. So one way to think about it, adding the same number to both sides of an equation, that is equivalence preserving. Multiply or dividing both sides by a non-zero constant value is equivalence preserving. Distributing, like we did in this first step, equivalence preserving. Combining like terms, equivalence preserving. Now you're probably saying, well, what are some non-equivalence preserving operations? Well, imagine something like this. Let me just start with something very obvious. If I said that x is equal to 2, a non-equivalence preserving operation is if I were to add or subtract or multiply or divide only one side of this equation by a value. Let's say I only added 1 to the left side. Then I would have x plus 1 is equal to 2. And it is not the case that anything that satisfies this second equation satisfies the top equation, or vice versa. X equals 2 clearly satisfies the top equation, but it doesn't satisfy the second one. That's because we did a non-equivalence preserving operation. Likewise, if I only multiplied the right-hand side by 3, I would get x is equal to 6. Well, by only multiplying the right-hand side by a value, it's not the case that anything that satisfies x equals 6 will satisfy x equals 2. That is somewhat obvious here. Now, there's a little bit trickier scenarios. Let's say we have the equation 5x is equal to 6x. Now, one temptation is, well, I want to do the same thing to both sides. I could just divide both sides by x. What will happen in that scenario? Well, if you divide both sides by x, you could think that an equivalent statement is that 5 is equal to 6. And you know that there's no x for which 5 is equal to 6. You can't make 5 equal 6 or 6 equal 5. And so this would somehow make you imply that, okay, there's no x that can satisfy. If you assume that these were equivalent statements, you'd say there's nothing that could satisfy 5 equals 6, so maybe there's nothing that satisfies this top equation. But this actually isn't an equivalence preserving operation, because you're actually dealing with a scenario where x is equal to 0, and you're dividing by 0. And so you have to be very careful when you're dividing by a variable, especially if the variable that makes that equation true happens to be 0. And so in order to be clear that you're preserving equivalence here, the way that I would tackle it is I would subtract 5x from both sides. And if you do that, and that is an equivalence preserving operation, you could subtract that expression from both sides, or that term from both sides, and then you would be left with 0 is equal to x. And now 0 equals x, and 5x equals 6x. These are equivalent statements. They are equivalent equations. Anything that makes this one true is going to make that one true, and anyone that makes that one true is going to make this one true. Now, one last thing, you might have heard me say you can multiply or divide by a non-zero value, and that's going to be equivalence preserving. And hopefully you just got a sense of why dividing by 0 is not a good idea. In fact, dividing by 0 is always going to be a strange thing, and it's undefined. But also multiplying by 0. For example, if I had, let's say, actually let me start over here. If I had 2x is equal to 6, and if I were to multiply both sides by 0, I would get 0 is equal to 0. And 0 equals to 0 is true for any x. 0 is always going to be equal to 0. But the problem is that first statement isn't true for all x. It's only true for x equals 3. So these two are not equivalent statements. They have a different set of x's that will satisfy. And so you have to be very careful when you're dealing with things that are either are 0. You can add or subtract zeros. Obviously, that's not going to change things much. When you multiply both sides by 0, you can start getting things that are not equivalent statements. And when you multiply or divide by things that could be 0, like variables, that also is a dangerous game to play. What do you think about the notion of equivalence?
一陣間，一陣間。
我啱啱用天靈掃大，就我係個天靈咁想抽你嘅。玩到咁就玩。
咧就佢可以 control 佢哋去到邊度。
I can control it.
而且佢有一個 distance，你可以咩？即係你可以從呢度一路行到嗰度，佢都一直係咁樣行。
佢有呢個 like time limit on how
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 far
long he can stay.
啊
And then until佢一定要做嘅。
咁中間有啲咩？佢哋係咪可以穿過晒所有嘅嘢㗎？包括 building，包括人。
其實I could use 佢可以 like main 佢啲嘢太傻啲。And I don't know how to upgrade it. No.
We need stories. We need stories to unstop ourselves. We're the only.
隻腳都係，有隻長空咬到成腳都係。
啊，你知唔知道你中意人邊位？
你嗰啲鑽石嗰啲嘢，好似 diamond 嗰啲嘢咧，你係可以睇到我嘅隱身㗎，係嘛？
嗯？Oh. No problem.
你有好多你知道嗰啲嘢，可能比較專業。That's the thing that's here, how about? Oh.
We're asked to solve for p, and we have the inequality here. Negative 3p minus 7 is less than p plus 9. So what we really want to do is isolate the p on one side of this inequality, and preferably the left. That just makes it a little bit easier to read. It doesn't have to be, but we just